Hi guys. So in statistics 2, you all know very well that we have mainly two parts in our syllabus. The first half was related to hypothesis testing and the half was where we learned about regression. Okay, so today we'll be mainly focusing on regression, and in order to start off with that, let me give like a brief understanding on what correlation is, because we start off with correlation and then move on to regression. Okay, so if I give an example, let's take something like marks. The marks I get for stats and the study hours, the number of hours I spend studying for the exam. Okay, now these are two variables and I want to identify whether there is a relationship between the variables. That means if I increase my study hours, is my marks gonna increase or decrease? That's the question I have. So in order to see whether there is a relationship between these two variables, there are several techniques which we can use. So the first one, easy one, is to visualize the data. So for that we use something called scatter plot. So we have already collected data, right, regarding the study hours and marks. So study hours would come over here in the x-axis. Why? Because that's the independent variable. And marks will come over here because that's the dependent variable. Okay, and if I plot the points, that means if I plot the data which I've collected like this, then this is called a scatter plot. So here each point on the scatter plot is like a single observation. That means this is the study time spent by one person and the marks that person has received. This is the number of hours the person has studied another person, and this is the marks that person has obtained. Alright, so each point shows single observation. And one thing which I want you all to be reminded of is, now x we call it as independent variable, but there are several other names which we can give for that. So sometimes they may say explanatory variable. Then we might also call regressor, predictor. So these are different terms which we use for the same thing. Likewise, for dependent variable, we may call it the response variable, regressor, regressand, and predicted variable also. That also can be applied. Okay. So this is basic tool of visualization, right? So based on the shape of the data points, the plotted points, we can identify relationships. So if I draw a scatter plot like this, okay, then is this positive or negative? Does this show a positive or negative relationship? Positive, right? Because when the x values are increasing, the y values are also increasing. Now this is specifically called a strong relationship because the points are close to each other. So if I draw a line, the points are close to each other. But however, if I draw something like this, okay, this is also upward moving, but the points are a bit far away. So that means this is a weak relationship. Now if I draw something like this, on the other hand, what can you say about the relationship? When x is increasing, y is decreasing. That means there's a negative relationship. However, this is a strong relationship, and if I draw something like this, again, this is also a negative relationship, but however, the points are a bit far away, making this as a weak relationship. Okay, weak negative relationship. Now, if I draw something like this, there is no particular shape which you can observe. Therefore, we cannot actually specify the relationship over here. If it's something like this, now the ones which I drew before, these ones 1, 2, 3, and 4, these are called linear relationships because you can fit a straight line for that. However, if I draw something like this, okay, you see that there is a shape, but it's not a straight line. If I give another example, okay, the plotted points are something like this. Okay, so the if I fit a line, it's going to be like this. So this is not a straight line, but however it shows a relationship. So these are called nonlinear relationships. So basically using a scatter plot, we can get a rough idea of what the relationship is. Now, if I take this one right here, the first one, okay, I know that this is a strong relationship and a positive relationship. But can I tell anything about the degree of strength of the relationship? No, right? That's not possible. So, in order to get like a specific value for the relationship, like a magnitude, what we use is there are two other techniques which we use. So, that's one is called covariance, and the other one is called correlation. Okay, so what we mean by covariance is where we measure the relationship between two numerical variables. Alright, so here the important things are we have to remember that this always measures linear relationships. That means if it's a non-linear relationship, covariance will be 0. And here we only deal with two variables. We can't apply more than two variables. And definitely those two have to be numerical. That means we should be able to quantify in numerical terms. Can't use categorical variables like taste and gender and color. Those type of variables we can't include in order to find the covariance. Okay, so the covariance equation goes like this. Covariance between the x variable and y variable is x minus x bar, y minus y bar. We take the product of it, that means multiply and get the summation sigma and divide this by n minus 1. This is the covariance formula. So if the covariance value of covariance is greater than 0, that means we can say that this shows a positive relationship between the two variables. Okay, then if the covariance is less than 0, that means there is a negative relationship between the two. If we say that covariance is between x and y is equal to 0, this can either mean two things. One thing we can say there is no relationship between the two, or we can say no linear relationship. Why is that? Because as I said before, in covariance, it only measures linear relationship. So if the relationship between the two variables x and y is a non-linear relationship, still, although there is a relationship, the covariance will give a result as 0 because the same reason. It can't measure non-linear relationships. Another thing which I have to keep in mind is covariance. It can range from minus infinity to positive infinity. Alright. Now the problem which we see in covariance is that it's dependent on the units of measurement. That means, for example, if I say I'm going to find the relationship between covariance between marks and study hours. And marks and the interest in the subject. So let's say we measure the study hours in terms of hours and interest. I've asked everyone, each and everyone, how much marks, how much points you give in a scale of 1 to 10 for your interest in the subject of stats. So I'll give it like points here. So definitely both are different units of measurement. So when the units of measurement are different, the covariance value which we get from these two, let's say this is 55 and this is 100, we can't say that the relationship between marks and the interest on the subject is, it has a much more strong relationship strong positive relationship than study hours and marks, because since the units of measurements are different, we can't actually compare the two. So the main disadvantage over here is if the units of measurement are different, then we can't compare. So in order to resolve this issue only, there's another technique called correlation. So in correlation also, we basically do the same thing. We identify the linear relationship between two numerical variables. So here it gives an indication about the direction. It states whether there's a positive or a negative relationship between the two variables, and it also gives an indication about the relative strength. And therefore, this ranges within -1 to +1. So if I draw a scale over here, okay, this is 0, this is +1, this is -1. Okay, so this point over here we can say this is perfectly negative. If our correlation is -1, it's perfectly negative, and if it's +1, it's perfectly positive. If it's 0, what would we say? Either no correlation, or it can be a nonlinear relationship. Alright, and if the correlation is around more than 0.75, let's say, if it's more than 0.75, now this is 0.5, right? 0.75 will come over here. Then we can say this is a highly positive relation. This indicates a highly positive relationship. Likewise, on the other side, if it's less than -0.75, we can say this indicates a highly negative relationship. If it falls within this region over here, we can say there exists a moderate relationship. This is a moderate negative and this is a moderate positive. So whatever which falls in this region over here, what does it mean? Definitely weak. Weakly negative and weakly positive. So there are basically several formulas to find the correlation. So to move from covariance to correlation, what we do is we take the covariance x and y and divide this by Sx, that is standard deviation of x, and standard deviation of y. So standard deviation of x is like sigma x minus x bar whole thing square over n minus 1, since its standard deviation is a square root, and sy is given like y minus y bar whole thing square over n minus 1 square root. These formulas will definitely be given in the exam, so you all don't need to worry about that. You all just need to know what are other formulas and where are we supposed to use it. No need to memorize this stuff. Now I was telling about the units of measurement, right? So over here, now let's say x is measured in meters, y is also measured in meters. So the numerator is, we can say it's in meter square, right? Now at the bottom denominator, this is x is measured in meters, y is measured in meters. So again in the denominator we have something called meter square. So in correlation this gets cancelled off, and that's why we say correlation is not affected by units of measurement, and therefore we can compare. Okay, so here It's not affected by units of measurement, which makes it possible for us to compare and do analysis. Now, other than this, you all have to remember certain facts like, okay, just say we took marks and study hours, no? And the correlation which I got was 0.8. Okay, so that this indicates a positive and a strong relationship between the variables, right? So just because this is a strong correlation, this does not, now I'll write that down, this is a strong correlation. Everyone will agree with that, right? But just because it's strong, this does not indicate that X causes Y. In correlation, we never talk about causation. That is not what we are focusing on. And let's say just because there is a weak relationship between some two variables, it does not indicate there is no relationship. Weak correlation. I'm sorry, this I meant this to be 0. Okay. Just because this is like a 0, this does not mean there is no relationship. There is a possibility for this to be a non-linear relationship, because in both covariance and correlation we deal with linear relationships. So these points you all have to remember. And other than that, what I wanted to say was, okay, let's say there's a strong correlation between two variables. This can be caused due to many other reasons. One can be due to chance. That is what we are focusing on. That is what we are trying to measure. But it can also be caused by causation. Though we don't say necessarily say that correlation indicates causation, causation might be a reason. Okay, I'm saying might be a reason for a strong correlation. And the third factor is maybe because of another variable. Now here we took only marks and study hours, and we found a positive relationship of 0.8. Okay, but sometimes marks can be increasing not because of study hours but because of some other reason, because of the expertise of your teacher, okay, the experience of the teacher, or maybe the interest you have on the subject, or maybe the motivation given by your friend to study the subject. Okay, anything. There are so many other variables which can affect the dependent variables, but you haven't included that when calculating the correlation, right? So because of third factors, or third, or I can say unseen factors, also this might be a positive relationship. So these things please keep in mind. So in order to identify and analyze the relationship, what we took first the scatter plot, right? First that's the basic visualization technique which we use, scatter plot. So in scatter plot, it's very easy to look at the thing and say whether there is a relationship existing or not. But the thing is, we can't measure. There is no numerical terms attached to it. So because of that reason, we move on to something called covariance. So covariance gives us a magnitude and a direction for the relationship between the two variables. But what's the problem it has? Covariance, only if the units of the measurement are same, then we can compare the two. If not, we can't compare. Therefore, we move to something called correlation. Okay, so correlation, it's free of units of measurement. That means you can measure one thing in meters, other in kilograms, or other thing in seconds. Anything is fine. It's not gonna affect the answer you get, the relationship you find at the end. Therefore, we can make comparisons between different variables. Now after correlation, we move on to something called regression. Why is that? That is because correlation, the R which we find over here, this cannot be used to make prediction. This is just a summary statistic. We say it's a summary statistic which summarizes like the strength of the linear relationship. Here we summarize the strength of the linear relationship between just two variables which are numeric. Right? This is what we do in correlation. If I take x as the mark, x plus my study hours, right? X as study hours and y as my marks. My correlation was R was equal to 0.8. Now let me interchange this. I am gonna take marks as my x and study hours as my y. Still you'll get the same correlation coefficient. That is because it doesn't consider what is independent and dependent. Because of that reason, you can't do any predictions, because to make a prediction, you have to give an indication of what is dependent and what is independent. Because of this only, this has happened. So, without knowing what is dependent and independent, you can't use that for prediction. So, that's the main disadvantage in correlation. And another thing is, here we only deal with two variables. As you can see here, we only deal with two variables. That means we are saying only this factor is causing, no, sorry, here I made a mistake. We never use causation in correlation. We are saying this is the factor which might be affecting study hours, is the only factor which might be affecting marks, but we are not considering the other variables. So that is another disadvantage over here. So because of that reason, because of the inability to use this for prediction, we have to use another technique called regression. So that's basically correlation, guys, for the starting bit. Alright, so now let's start off with regression. So in regression, there are different types of regression. First, we'll be specifically looking into simple linear regression. Alright, this is also called the bivariate regression. Why is that? We'll see. Okay, so what we mean by linear is, you all very well know that we are trying to fit a straight line like this, or this some straight line. So this is y equals mx plus c, this kind of an equation only we are trying to fit over here. What do we mean by simple? There is only one independent variable. Independent variable are denoted by iv. Okay, then why do we call it this as a bivariate regression? There's only one independent variable now. That's because altogether there are two variables. That is one independent variable and another dependent variable. Okay. Actually, when we are forming a regression, it can take any form. It can be linear, non-linear, anything. But this linear is considered to be the simplest form. And in linear also, here we are considering only one independent variable, which makes it simple. If there are more than one independent variable, then we call it as what? You all know, multiple linear regression. Okay. Okay, so let me explain this through an example which I have over here. So here, as you can see, this is the population data which I've collected from some households. So altogether there are 1, 2, 3, 4, 5 this way and 5 this way. So 25 households. So what I've done is I've gone to 25 houses and asked their income and their corresponding monthly consumption expenditure. So income is X and expenditure is Y. So as you can see over here, 100, 150, 200, 250 and 300 is their income. So there are 5 houses under each income level. So although, for example, let me take this one, will you? 100. So there are 5 houses with income level of 100. So even though their income is the same, do you see that their consumption expenditure is also the same? No, it's different. One is having 80, another one 70, 55, 75, 65 likewise. And if I take 150, you see all these houses, all these 5 houses have the same income, but however their consumption expenditure is different. Okay, so now if we analyze this, you can very well see that when the income is increasing from 100 to 150, what can you say about the consumption expenditure? The expenditures which was in the range of 50 to 80 has now increased to the range of 100 to 140, right? So likewise, if I increase again, this has increased. When income increases, consumption has increased. So basically, by looking at the data or the table, you can get a rough idea that when the income increases, Y is also increasing. But now if I ask a question like this, what do you think about the change in consumption expenditure because of an increase in income by 1 rupee? That is like, if I put it down, when monthly income increases by 1 rupee, what happens to the consumption expenditure on average? Okay, so if I ask a question like that, you all won't be able to directly answer. Because see, and even though the income is the same, within the same income level itself, there are different expenditures. So at this point of time, I think it's better to get a mean value for each income level. So if we take this, when the income is 100, if you add these 5 expenditures and get the average, you will get 69. Okay, so what are we trying to say from this? If the income level of a house is 100, they are basically expected to spend an average of 69,000 for their consumption. Likewise, we can find the average for all the income levels. So here you get 120, here you get 173, 225 and 271, which indicates basically the average consumption expenditure if you have that particular income level. Now if I go and plot this in a scatter plot, it will look like this. So here we have the x and y variable. Up to 300. Again here 50, 100, 150, 200, 250 and 300. So when the income is 100, these are the expenditures. So it will be somewhere over here. There will be 5 dots. Sorry. Then when the income is 150, it will be somewhere here. Then here. Here and here. So these are basically, this is the population data which I have plotted. Now if I mark the averages which I have got, that is this 69, 120, 173, 225, 271, I get a straight line. And this straight line is what we refer to as population regression line. That is equal to y is equal to beta naught plus beta 1 x. Why did I write like that? Because when it's a straight line equation, obviously the equation is y equals mx plus c, right? Mx plus c. So over here beta 1 is our m and beta naught is our c, the slope and the intercept. So how do we interpret these two? Beta naught I said this is the intercept. So this indicates the mean or the average value of y when x is 0. Why do I specifically say this is the mean or average value of y and not the actual value of y? Because see, this value over here, what is that? It's 69. This is 69. Do you find that 69 in the population data which I have given? No, it is the average of all these values. So that's why we say here it's the mean or average y when x is equal to 0. Okay. Likewise, slope also you interpret like the same way. So we say it's the mean or average expected change in y for a unit change in x. Here again, these value over here which you have got cannot be observed in the actual data. It's what we have calculated using this average value. So this would be a population regression line. Y equals beta naught plus beta 1 x. Now you all might wonder where we learned something called the error term. Where is that error term? Okay, I'll come back to that. So as you can see, now let me take one data point in given over here. Let me take this 80. So 80 is represented by this dot, this red color dot, right? So does this 80 fall on the regression line which we have constructed, the green color population regression line? Does it have this red color dot? No. It is beyond the line, right? The dot over here is beyond the line. That means the equation for the population regression is not this. This is the equation of the line, not the model. Because the model has points above and below the line which we have constructed. Okay, if you take this 80 comprises of two things. This 69 plus, what is 80 minus 69? 11. So 69 is the average value which we got. Average value of y when x was 100. And this is a difference which we call the error term. Together we get the actual value of y. Okay, so this is how the population regression equation differs from the population regression line. So because of certain factors, actually when the income is 100 over here, let me highlight that and show. When the income is 100, actually you should have got 69. That's the average value. But you are getting a value of 80 that is beyond the line because of reasons or factors other than the variable which you have included in your regression line, driving them beyond or below. So how you write your population regression equation is yi equals beta naught beta 1 x plus the error term. What is the name which we give for this? This is the population regression equation. And this is the population regression line which I have shown over here. Okay, I hope you all understand the difference. Population regression line only consists of the average values of y. Then if we add or deduct the error term, then we get the population regression equation. And that's why our model has this error term over here. So in maths, we haven't learned about this error term. We have only learned this part of the equation, which is y equals mx plus c, the straight line component. But in stats, we have something called the random error component, which drives the points away from the line. Hope you all have got a clear idea of how the population regression model works. Now in reality, although we have collected over here, I have a table of the population data. I mentioned that this is hypothetical. This can't be obtained in real life because it's going to be either very hard, time consuming, costly, all those factors are there. So because of that, we will only be able to collect a sample of data, sample of items, and from that we will be predicting the value of the population values. Okay, so if I take a sample from this data population, let's take random values. So under income level of 100, I'm taking 75. Then let me take 120, 195, 220 and 260. Now if I plot these points, I'll be getting the what? I'll be moving on, since I'm using the sample data, I'll be able to get the estimated regression line or the sample regression line. So I'll move to the other page since I don't have space over here. So what were the values which we had chosen? When x was 100, 150, 200, 250 and 300, the y values were 75, 120, 195, 220 and 260. Now let me draw that. Hundred fifty, 200, 250 and 300. So when it's 100, this was 75. Then 150, it was 120. Then 200, 195. 250, it's 220. Then when it's 300, we got 260. Okay, so these are the sample data. Now for population, we were able to easily fit the line, right? But in sample, it's not that easy to fit a straight line because the points don't exactly fall on the line. So we have to apply some technique so that the points are much as close to the line which we are trying to fit. Okay, so there are two methods for that. One is called the freehand method. So in freehand method, what you do is by looking at the points, you draw a line making sure that it's much as close as possible to the line which you have drawn. So the distance between the points and the line should be minimal as possible. So this is called freehand method. But the disadvantage in freehand method is now I am drawing something like this. But if I ask someone else, that person might draw something like this and say, why my line is also very close to the points now. Then another person might draw a line like this and say, even mine is very close to the points which you have drawn. So in that case, this means it is not unique. Person to person, it's gonna differ. That means we can't use this for further analysis. No point at all. So we have another method called OLS, ordinary least squares method, which is like a scientific proven method which is used to fit the regression line for the sample data. In OLS, what we do is same thing, the same concept. We find the closest line to the points in order to minimize the distance from the point. So if I could erase this, okay, if this is my line which I'm gonna get from OLS, OLS will make sure that the distance between these points and the line is minimized as much as possible. Okay, the predicted line, usually how do we write the predicted line? You all now very well know how do we write the population. Okay, population is y beta naught plus beta 1 x plus the error term. Okay, in sample, it's the predicted line. So we put a cap for everything. Beta naught cap, beta 1 cap x. And do we have an error term? No. That is because the reason is we are trying our best to minimize the errors as much as possible. So we assume or we think that over here error is minimized. Actually, now what's the formula for this error? Before anything, I want you all to know that actual values, these yellow color points are denoted by y. And this fitted line, as I said, this is y cap. So the green color curly brackets is my error. So what is the equation for my error? My error. Another thing which I want you all to remember is when I said error only, I also remembered. We use the word error in population. When it comes to sample data, we don't continue to use error, but we say it's a residual. Okay, so over here we are going to find the residual and not the error. It's the same, but the terms are different. Alright, so residual, what's the equation? It's the difference between y and y cap. That is the actual value and the predicted value. Actual minus predicted gives us the error. Y minus y cap. So the sum of these errors, I can say sigma y minus y cap. This is the one which we are supposed to minimize. Alright. So when minimizing, what happens is that because of certain issues, we have to make this as a positive thing. So either we have to find the absolute differences. What is an absolute difference? You put modulus. So what, even if you get a negative number inside, you consider it as positive. Or either you have to square this. So if you square, it's y minus y cap to the power 2. Another important point which you all have to remember is, guys, what we mean by minimization. So minimization is simply we are finding the differentiation and then setting it equal to 0. Equals to 0. Okay, so we'll be minimizing this one, right? So if I go ahead and do that, we have y minus y bar error. This is the sum of errors. We have to minimize this. Since we can't, we found the sum of squares of the errors. Now I said minimizing is differentiating and setting it equal to 0. So over here, if you all, I know that you all remember, y cap, I can write this as in a different way. Because y cap is a prediction line, right? It's beta naught cap plus beta 1 cap x, right? So over here, instead of y cap, I can write beta naught plus beta 1 x. Yes? Yeah. And if I simplify, it will be beta naught minus beta 1 x. This whole thing to the power 2, this only we are supposed to minimize. So since there are two independent variables, we will have to apply partial differentiation. So first we have to differentiate or derivate in terms of or with respect to beta 1 and then with respect to beta naught and beta 1. So first one, if I differentiate, this is the error term, right? I'm gonna differentiate the error term with respect to beta naught. So I hope that you all remember we did this in calculus. How do we differentiate this? partial differentiation, this is a chain rule. So first what we are we take this 2 in front, we bring this 2 to the front and write the same thing inside the brackets, and then we differentiate this inner function. So that's gonna be with respect to beta naught means y is gonna be 0, beta naught is gonna be -1, and then beta 1 is gonna be again 0. We're gonna set this equal to 0, that is differentiation. Then with respect to beta 1, again we write the 2 in front and write the same thing inside the brackets and derivate the inner function with respect to beta 1 right now. So see, y is a constant, so 0, then again 0, then we have an x over here, so that's going to be minus x. This is equal to 0. So now we have two equations, simultaneous equations, and if we solve the two simultaneous equations, we can get the equation for beta 1 and beta naught. What is beta 1? Beta 1 is our slope. So you will get x minus x bar. There are actually different, so several formulas I can say to find the same thing. But anyway, it will be provided in the exam now. So you all are supposed to know how to use the formula only, not to memorize the formula, but how do we use the formula in order to get the answer. And beta naught is simple. You get the mean of y, beta 1 into mean of x. Okay, as simple as that. So since you have found beta 1 and beta naught, now you can form the prediction line, which is y cap equals beta naught plus beta 1 x based on the values which you get. Okay, now let's go ahead and do an example and see how to interpret these values. Y equals 40 plus 2x. So x is the study hours and y is gonna be our marks. Okay, so what does this 2 mean? When you increase the number of study hours by 1, your marks will increase by 2. So if I write that, when number of study hours increases by 1 hour, marks is expected to increase on average by 2. This is the slope. What is this then? This we call as the intercept. So that is this shows the marks we get, marks obtained by students when he or she doesn't spend any time studying. That means basically study time hours is 0. This is the intercept. So in the question they will give if they give the x value based on, let's say one person has studied for 10 hours, that means her marks is gonna be 40 plus 2 into 10. So even though she has studied for 10 hours, she's only gonna get 60 based on the equation which I've given. Now when predicting, there are two terms which you would have come across, that's called interpolation and extrapolation. Interpolation, extrapolation. In interpolation, what we do is we are going to substitute a value for x based on the range which we have used to construct this y equation. So let's say we have got this equation using these values. Okay, this is our sample data. Okay, our sample data goes up to, this is our study time hours and this is the marks, right? Okay, so in our sample we have people who have studied 1 hour, 2 hour, 3, 4, 5, 6, up to let's say 10. Okay, now if I'm substituting 8, that means this is something within the range of our data. Our range of data goes up to 10. Okay, so since 8 is within the data set which we have used to construct the equation y equals 40 plus whatever 2x, this is called interpolation. If we go beyond this point, if we go beyond this 10 and say, let's say we want to find the marks of a person who has studied for 16 hours, then that is called extrapolation. Now we say that extrapolation is a bit not reliable. It is less reliable when compared to interpolation. That is because, let me give like an example for that, for you all to understand this very quickly. So now you all know this, consider this as years, okay, and consider this is as tourism save earnings. Now this is 2017, sorry, 16, 15, 16, 17, 18, like that. So now we have constructed an equation. Let's say this is our equation for tourism earnings, 1000 plus 50x, based on data which we have up to 2018. So our equation, our graph would look something like this. Okay, now if we had done extrapolation, we would have expected this to show an upward trend over here. So if we had found what will be the tourism earnings in 2025, it will show an increased amount like this. But actually what happened in the context, in reality, after 2018, what happened? The Easter bombings happened and then Corona came, and as a result the earnings fell, right? But we couldn't predict that at the moment. We had information only up to 18, and based on that information we expected an upward trend. No one even expected this to go like this, but this is the reality. This is what happened. So this is the risk of using extrapolation. Since we can't definitely predict the future with certainty, there is a bit of risk involved in applying extrapolation. However, interpolation is very reliable in comparison to extrapolation. Next, what we have is measures of variation. So before I move on and give you all the formulas of that SST, SSR, SSE, let me draw like a graph so that you all don't need to memorize any of those formulas. If you all simply remember this graph, that would be enough. More than enough, I would say. Okay. So this is a graph. We have the plotted points. Okay. These are our plotted points. And then we have the predicted line going like this. Okay. Then we have something called the Y bar line. What is Y bar actually? Y bar. Y bar is the sum of y divided by n. So it's going to be a constant figure. So if we add all these dots, blue color dots together and divide it by n, the number of observation, we will get a value. Let's say that is going to be like this. So if I take a point, this one, let's say this one, the distance between this y, the actual value of y, and this green color y bar is what we refer to as SST. That means the variation from the mean value y bar is what's denoted by this blue color. The actual value y has moved beyond this y bar value by this SST. Now SST comprises of two things, two components. If you all have noticed, there is this one component over here. This is called SSR. Why? Because now this is the predicted line. The red color line is the predicted line. And below the predicted line, the variation is explained by the line itself. Okay, so since it's explained by the regression line, we call this SSR, which indicates the explained variation. What about this then? This is what we call SSE. Actually, if we had, now let's say study hours and marks again, if we had studied this many hours, okay, this many hours, we should have ideally got this marks based on our predicted value. That means based on the x, we have predicted the marks to be over here. But however, is that what has happened? No. The blue color point has moved way beyond that black color point. That means some other variable or some other factor has caused the blue color point to move upwards and not to be in black color point. Something other than this x variable has been the reason for it to move up, causing an error. So that's this error. So in regression, we have total variation of SST that's divided into two components, SSR and SSE. If you all want me to explain in a simple manner, you all know what is variance, right? What is variance? What's the formula for variance? Y minus y bar whole thing square. This is the numerator. Let's forget about the denominator, that's n minus 1 or n or whatever. Let's forget about that. Just consider the numerator. It's y minus y cap. So basically that's the SST, right? SST shows the total variance. Y minus, you all don't have to memorize over here. This is the actual value and you're subtracting the average. If you find the square root for this, the square for this, square it out and find the summation, you'll get SST. Then when it comes to SSR, that is also simple. What are you trying to do over there? You're finding the variation between your predicted value y cap and the average value y bar. Then you find the square and sum. Then it's the error. So how does error occur? Error occurs when your actual value is above or beyond your predicted line. Predicted line is y cap. So if you take the square and find the summation, you'll get SSE. So the total, as I said before, total variation comprises of two things. This is the explained variation because y is covered by the regression line, and yellow color one is the unexplained variation. Now you all tell me guys, when is the model a good fit? When the explained variation is more or when the unexplained variation is more? You all are correct. When the explained variation is more only, that means what we are trying to say is the x variable which we have considered the independent variable is explaining most of the variation which is occurring in y. That is good, right? So that's why we have something like a measure called coefficient of determination. So let me erase this off. This is the variance formula, right? I'll erase this off. So we have a measure called coefficient of determination, R square, basically, capital R square. R square is denoted by SSR over SST. That means out of the total variation, what's the percentage of variation explained by the regression line? So as you all have correctly thought, When the explained variation is more only, this model is like a good fit. So when SSR increases, R square increases, indicating that this is the good fit for the model. Alright. So if I've got an answer like zero point 0.7, that means 70% of the variation in Y is explained by X. Okay, so for example, if X was study hours and Y is marks, we would say 70% of the variation in our marks is explained by the study hours. Alright, so R square can be found in another way also. If I had taken SSE over SST and subtracted this from 1 also, it's the same thing. Because now let's say SSR over SSE is 0.7. So SSE over SST would be 0.3. And if you subtract that from 1, you will get 0.7. Okay. So as far as the coefficient of determination is greater, it's very good. And we can say the model is a good fit. Usually, coefficient of determination, we expect it to be more than 0.7. So it falls within the range of 0 to 1. So if it's more than 0.7, we say that it's a good fit. There's another equation for that. Please go through from the slides, because there are several equations which we can use to find the same thing in regression. So I ideally or basically depends on what the lecturer is gonna give for the exam. Alright. Other than this, we have another small concept called standard error of estimate. Standard error of estimate is basically this, it's like the standard deviation. So as I told before, standard deviation, how do we find? Y minus Y cap, that is the actual Y minus the mean Y, right? Mean Y to the power 2 sigma divided by the degrees of freedom. Likewise here also, we can, instead of writing this, I can now write what? You all might say SST. That's wrong. That's because in regression, what we mean by standard error of estimate is not the standard deviation around the sample mean, but it's actually the standard deviation around the prediction line, which means this is not Y bar, prediction line is Y cap. So this is not SST, this should be ideally SSE. SSE divided by the degrees of freedom. So the degrees of freedom is n minus 2. Why do we say n minus 2? Because our prediction line, you all know our prediction line, like y cap equals beta naught plus beta 1 x. How many unknown constants are there? We don't know beta 1, we don't know beta naught and beta 1. So there are two ways. Because of that, the degrees of freedom will reduce by 2. Okay. So this is how you find the standard error of estimate. Don't forget to put the square root. SSE over n minus 2 square root. So basically what does it show? It shows the variation of actual y values, that is y, from the predicted y values, which is y cap. Not the mean y values, but the predicted y values. Remember that and keep that in mind. So this is how we use SST, SSR and SSE into concepts called coefficient of determination and standard of error of estimate in order to derive good decisions or something like that. Guys, another thing, remember SST is what comprises of SSR and SSE. So we can write this as SST equals SSR. I hope you all would have got that anyways. So if you all don't know SSR, but you all know these two, then you can easily find this. Let me quickly explain what is meant by adjusted R square as well. So coefficient of determination, that is R square. Now we have something called adjusted R square. So what happens is this is basically used in multiple linear regression, but I'll explain it here itself since we went through R square. So what happens is when you have limited data, let's say I have a sample and that sample comprises of 4 numbers 1, 2, 3 and 4. Alright. Now I'm having an independent variable, and because of that my degrees of freedom, which is n minus k plus 1. I hope that you all know what is degrees of freedom. What do? We take the sample size and we reduce the number of independent variables by adding 1. Because now let's say for example this is a simple linear regression beta naught plus beta 1 x. Alright, this was a simple linear regression, and over here in order to find the degrees of freedom we said it's n minus 2. How did this 2 come? Because we have beta naught and beta 1. So when there is one independent variable we deduct k plus 1. 1 plus 1 2. Okay, so here degrees of freedom will be n minus 2, that is 4 minus 2 is 2. Now if we increase the independent variable to 2, this is gonna be how much? 1. Now if we increase it further, degrees of freedom is gonna reduce to 0. So as you can see, when I'm increasing the independent variable, the degrees of freedom, so what do we actually mean by degrees of freedom? Basically it indicates how much independent information goes into an estimate. Okay, so if we want a lot of independent information to go into a parameter estimate, like we get a precise estimate and carry out a powerful hypothesis test, we need our degrees of freedom to be greater. Okay, but here as you can see, when that independent variable is going up and it's increasing, the degrees of freedom is going down. So when the degrees of freedom is going down, if you take a standard error of estimate, what was it? SSE over n minus 2. So in multiple linear regression, I can say it's n minus k plus 1. Okay. So when the degrees of freedom is increasing, our standard error of estimate SYX is gonna go up. So results are not gonna be independent anymore. It's gonna be less precise and model would poorly perform because of this. But this is not actually captured in our R square. When you increase the independent variables, R square is gonna increase. But however, is that the case? The precision decreasing is not captured in the R square. So that's why we compute something called adjusted R square. So adjusted R square, the equation goes like this. 1 minus R square n minus 1 over n minus k plus 1. So over here, when you increase the number of k's, independent variables, what will happen to your degrees of freedom? It's gonna go down. So when that goes down, this entire thing is gonna increase. So if you subtract 1 minus this entire thing, R square is gonna go down. So actually, adjusted R square penalizes the R square for adding more irrelevant independent variables for limited data. So it considers both the sample size n and the number of independent variables k. Alright, I hope that you have got the basic idea. So when you basically increase the number of independent variables in your model, your R square is going to go up. However, your precision is going to go down. Why? Because degrees of freedom is reducing. So the number of independent information which you're using to construct the model is decreasing. So that's not shown in this R square. That's why we find something called adjusted R square, which will decrease when your independent variables increase. Okay, so always R square adjusted is going to be less than your usual R square. You can see this, right? Yes. Now, how do you interpret an adjusted R square? Let's say you got an adjusted R square of 0.7. Then you say 70% of the variation in Y is explained by X after considering the degrees of freedom. So in your degrees of freedom, what you have? You have sample size n and you have the number of independent variables also. These two are considered. What is n? The sample size, and k is the number of independent variables. Alright. So this is basically it.